Hi, I'm June.
Hi, I'm Katie, and we're presenting on behalf of our co-authors on our paper in which we analyze the quality and stability of a streaming end-to-end on-device speech recognizer. Stability, or flickering, is when text appears on the screen and then it changes or disappears. Flicker in partial transcripts affects downstream applications and the usability of ASR models. We define stability as follows. When text grows, it's stable. When it changes, it's unstable. In the example chart to the right, from segment 1 to 2, the word come is added, that's growth. But when come changes to comma, that's unstable. These metrics are easy to calculate. They're independent of the final hypothesis or the ground truth. And there's a direct correlation between flickers and the downstream application receipt. We define stability with two metrics, unstable partial word ratio and unstable partial segment ratio. Unstable partial word ratio is a ratio between the total number of unstable words and the words in the final hypothesis. A segment is the partial result which is shown on the screen. Unstable partial segment ratio is a ratio of unstable segments to the total number of utterances. We show an example of tabulating unstable segment ratio and word ratio in the example to the right. But generally, word ratio correlates with the severity of the flicker, while segment ratio correlates with the frequency of the flicker. We investigated instability in the context of an end-to-end streaming RNNT model. In a typical hybrid ASR model, it consists of two components, the language model and the acoustic model. In the end-to-end model, we have analogous components, the encoder, which is similar to the acoustic model, and the predictive model, which is similar to the language model. Together, they are combined into one neural network and predict the probability of the next tokens. We used an end-to-end model that is streaming. The model architecture is similar to that described in the reference list here. The output partials are continuously streamed as input audio is fed into the model. We explored the idea of stability in a framework in which we optimized for an end-to-end ASR system. We operated within three general constraints: word error rate or accuracy, model stability, which we've defined, and speed of partial emissions. In other words, the time between partial emissions. We're using a streaming RNNT model that incorporates spoken punctuations, capitalizations, and numerics. Our initial balance favored fast results, a low interval between partial emissions, at the expense of stability, with a fairly good accuracy rate. We investigated instability and broke it down into two umbrella categories of causation. One is streaming instability and the other is text normalization instability. With streaming instability, the recognizer outputs a partial based on the information it has at the time, and as it gains more audio, it may correct the output to be more accurately reflective of the full audio. Text normalization, we broke down into a further few categories: capitalization, numerical, and spoken punctuation instability. Let's dive into what contributes to text normalization instability. One key point is spoken punctuation. Spoken punctuation we first represented as word pieces. So for example, if a user says exclamation, it would be broken into exclam and ation, and the word would first be transcribed as exclamation before then being retranscribed into an exclamation point. As you can imagine, this caused a lot of instability. Another text normalization major cause of instability was using mixed case training data. The mixed case training data interacted with word piece models and exacerbated instability. We can observe this in the table on the right. We first started with lowercase training data for both a grapheme and a word piece model. The instability rates were approximately equal. When we switched to mixed case training data, the instability rates of both rose. We then lowercased the outputs of both models, and we found that while the grapheme instability dropped back to baseline levels, the word piece model did not. This indicates that there's probably an additional interaction between mixed case training data and instability. We believe that the cause is actually a lack of diversity of the top n hypotheses in the lattice of the word piece model. In other words, the same word may be represented in both capitalized and uncapitalized form. Finally, text normalization instability can be exacerbated by multi-domain training data. When data is sourced from different places, there may be inconsistencies in punctuation, capitalization, and numerical formats. We came up with various strategies to reduce text normalization instability. To address numerical instability, we generated valid data using text-to-speech. We updated the model to correctly output numerical format. For spoken punctuations, we added spoken punctuation tokens to the model as singular non-space entities, such as exclamation mark or left curly bracket. We now predict the entire token as a whole, and it's immediately converted into a symbol before the token gets shown to the user. We also applied a capitalization normalizer to standardize casing and trading data. This makes data more consistent regardless of the data set it comes from. Finally, we incorporated domain ID into our data sources. We get a lot of different data from different sources, and domain ID helps the model to learn consistent text normalization within each domain. Next, we measured the effects of each strategy. As you can see in our results table below, the word error rate improved, and even the mixed case word error rate improved when we used our text normalization and domain ID. We reduced instability and word error rate by applying text normalization such that both were actually lower compared to the baseline. June is now going to talk about how we reduce streaming instability in our system.
To improve streaming stability of the model, we go back to the three categories that we're looking at: the word error rate, the speed in which we emit partial results, and the stability of the model. Previously, we mentioned that the initial model was sacrificing model stability for speed. And as we apply the bags of tricks that Katie has mentioned, seeing in the previous table that the word error rate and model stability both improve. In order to improve the streaming stability one step further, we can consider compromising one of the two other metrics that we were looking at. There is a huge body of work in speech community and machine translation community that considers sacrificing word error rate for the improvement of stability. Two of the works are cited here. Specifically, they want to expand from an already recognized or hypothesized segment in the decoding process, which means that the already hypothesized segments will never change. But there's another way to improve model stability, which is to sacrifice the speed of which partial results gets emitted. And we call this delaying partial emission. First, we would like to define what it means to delay partial emission and how we can measure it. In this case, partial emission interval is defined as the time in between subsequently emitted partial results. There are two ways to delay partial hypothesis. One is uniformly delay the partial emission. The other one is to use a threshold, which means that you first have a model that models the stability scores of each partial results. And if the score is above a certain threshold, you show the partial result to the user and the downstream. And if the score is lower than the threshold, you do not show it. We show an example here that uniformly increases the partial emission interval by 3 times. And hence, out of the 9 hypotheses, you only see 3. And because of that, the number of unstable partial words and the number of unstable partial segments decrease significantly. We first explore how the end-to-end RNT will behave when we uniformly delay the partial emissions. As seen from this graph on the right, let us first look at several definitions. So the blue curve, or the square curve, is UPWR, which measures unstable partial word ratio, and the red dotted curve is UPSR, which measures the partial unstable segment ratio. And the yellow triangular line is the mean partial delay. Mean partial delay is defined as the average latency from the detected start of speech all the way to the emission of the first correct words in the partial. The absolute value of the mean partial delay does not have a clear meaning because it depends on the length of the sentence, but the comparison of it shows you how much delay the downstream or a user can detect during the transcription process. In this graph, the x-axis is the partial emission interval. The y-axis is the ratio of the unstable words and unstable partials. Let's now compare the results of the partial emission interval of model G from 50 milliseconds to 200 milliseconds. What we are seeing is that at 200 milliseconds, the instability improved by almost 3 times. Not only that, we see an imperceptible user-perceived latency of the ASR system. There's a very reasonable mean partial delay increase. And this 200 milliseconds of uniform partial delay presented a significant stability improvement. We also explored the impact of stability when we threshold the stability scores. What it means is that we use an external model to estimate the stability of partial results. And if the stability score is beyond a certain threshold, we show it to the downstream applications and users. And if the stability score is below this threshold, we do not show it. We applied the logistic regression model to estimate stability as suggested by McGraw and Grunstein in 2012. And at a high level, they use features such as age, right context, or word level posterior. Age defines the length of time that a prefix stayed in the embed path without changing. The right context of the word is defined by the distance from the word to the end of the incremental result if we do the alignment of the word inside the result. As you can see from the figure on the right, the vertical axis again is instability, and the horizontal axis is the partial stability threshold. As we increase the stability threshold from 0.1 to 0.2, there is a precipitous drop of the instability scores. However, we see a sharp increase of the mean partial delay in this region, making it very difficult for us to decide which threshold is the best. To conclude, in this presentation, we first defined instability in terms of 2 metrics, a UPWR and UPSR. They quantify instability in terms of its severity and frequency. We further analyzed instability in our dataset and classify instability in terms of streaming instability or text norm instability. The text normalization instability is largely caused by the fact that we asked the end-to-end ASR to directly predict spoken punctuation, numerics, and capitalization. We further explored how word piece targets and the inconsistency in the multi-training data exacerbated the instability of the system. We developed various strategies to improve text norm instability, which include using punctuation tokens that captures punctuation words as one single word piece model target. We also use text normalization to ensure the consistency of casing in our multi-domain training data. We use domain ID as an input to our RNT encoder to enforce that the RNT learns the text normalization patterns in each domain. We also use text-to-speech generated numerics data for model fine-tuning. With these methods, we managed to improve the model instability without delaying the partial emissions or without hurting the word error rate. We also show how the model behaves if we delay the partial emission intervals. In this comparison at the end, we show how our final product looks like as compared to our initial baseline model. With a word piece target RNT at a partial emission rate of 200 milliseconds, we apply all these aforementioned methods to the training data and training process. We not only get better word error rate, punctuation error rate, mixed case word error rate, but we also lower the instability by a significant level. Thank you, and feel free to reach out to me or Katie if you have any questions.